Okay, so what if every single change you made to a piece of software wasn't just saved, but was actually proven to work the very moment you wrote it? Let's talk about a system called IISCV that does exactly that. And it does it by treating code not as a bunch of files, but as a living, verifiable history of successful experiments. Now, this isn't just about some new tool. This is a full-on mission statement. The goal here is to bring back a powerful, almost forgotten way of building software. We're talking image-based development, and to fix the one critical flaw that made it fall out of favor by adding a rock-solid built-in audit trail. So, to kind of get our bearings, let's compare the world most of us live in with the world IISCV wants to bring back. On one side, you've got file-based systems, like Git, right? You edit text files, you save them, you compile them, you run them. It's all about snapshots of text. But on the other side, you have image-based development. Here, you're not just editing files, you are modifying a live running program. The entire state of the application, the whole image, is what you're working with directly. Yeah, this image-based approach, it's kind of like a ghost from computing's past. I mean, it offers incredible power. You can change things on the fly, you can see results instantly, and you're interacting with your creation in a way that feels a lot more like sculpting than just typing. But, and this is a big but, it had a fatal flaw. And this was the Achilles heel. If you're constantly changing a live system, how in the world do you track what happened? How do you figure out which tiny change just broke everything? You see, without a clear verifiable history, this powerful way of working was just seen as too dangerous for serious projects. And that is the exact problem IISCV was built to solve. The whole philosophy behind IISCV is for it to act like a meticulous scientist's lab journal. Think about it for a second. A scientist doesn't write down every single failed experiment that blew up in the lab. No way. They record the procedures that worked, the results they actually achieved, and the conclusions they drew from that success. Well, IISCV does the exact same thing for your code. This whole process is called incremental substitution. And what it does is it totally replaces that old edit, compile, run cycle with a much more fluid conversation with your program. You evaluate code in the live environment. If it works, boom, it's in. If it fails, the debugger pops up. But, and this is key, nothing is recorded. This just fundamentally shifts your focus from managing files to curating a history of successful ideas. So what does this actually look like for you, the developer? Well, it's remarkably simple. You write a function in a special interface called an audit REPL. The system tries it out. If it works, a permanent auditable commit is created instantly and automatically, complete with its own unique ID. Failure is never recorded. Only success becomes part of your history. But you know, creating this history is one thing. Proving that the history itself is valid? Now that was the real trial by fire. The system had to be able to run its own tests to verify the entire chain of changes, right from the very beginning to the present. This is really the million-dollar question, isn't it? It's great to have a log of everything you did, but if you can't automatically go back through that log and prove that every single step is still correct, then the whole idea of an auditable history just completely falls apart. And of course, making the system verify itself was not simple. The first attempts were just met with this cascade of frustrating errors. First, the system couldn't even find its own audits. It was kind of like a librarian who couldn't find the library. So after fixing that, another wall, a super cryptic syntax error buried deep in the configuration. You know, this is the kind of problem that sends developers down a total rabbit hole of frustration, making you question everything you've built. And it all just boils down to that one all too familiar question every single creator faces when their vision just slams into reality. Why doesn't this work? And then, clarity. After all these complex attempts, the solution was right there in the documentation's FAQ section, a single, elegant command. Just placing this one little line of code in each test file allowed the tests to run themselves. All that chaos was over. The system could finally verify itself. So the system can now verify its own history? That's huge, but what does that really enable? Well, it unlocks a kind of superpower for debugging. Imagine a function that was working perfectly just suddenly fails in the live environment. This is where the beauty of IISCV really shines, especially when you bring in AI into the mix. The process for fixing a bug becomes incredibly elegant. First, a function fails at runtime, and the debugger opens up. But remember, no commit is made. The failure is just a temporary state. From a separate terminal, you can just ask the system, hey, what's the last good version of this function? And the system gives you the exact code. You then take that working code and the error message, hand it to an LLM and say, fix this. The AI gives you a corrected version, you paste that back into the repo, and a new, successful commit is created. The history never even records the bug, only the verified solution. It's amazing. Okay, this is amazing for a solo developer, for sure. But how on earth does this work for a whole team? I mean, if everyone is working on their own live image of the program, how do you combine all their work without causing just total chaos? Right. First things first, let's get the obvious but completely wrong solution out of the way. You cannot just merge two live Lisp images. It's a binary snapshot of memory. Trying to load one into another would be like trying to merge two brains. The result is just data corruption and a catastrophic crash. Don't do it. Instead, the system offers two pretty elegant solutions. The simplest and, frankly, the preferred method is something called named packages. Basically, each developer works in their own isolated namespace, so their code can't possibly conflict with anyone else's. Integrating is as simple as just loading their work. The other option is a micro-monolith architecture. This treats each developer's image like a totally separate server. It gives you complete isolation, but it also adds the complexity of a distributed system. This verifiable history also gives you this incredible safety net. If your main image ever gets corrupted for some reason, you can rebuild the entire application completely from scratch. You just start a fresh session, load the history file, and rerun every successful change in order. This proves that in this system, the history is the source code. And all of this makes IISCV way more than just a clever developer tool. When you have perfect traceability and automated verification for every single change, you're essentially automating the hardest parts of complying with really rigorous standards, like ISO. It provides objective, verifiable proof that the software was built correctly, step by step. And this really leaves us with a fascinating question to think about. We've spent decades building these complex systems to test our software after the fact. But what if the very act of writing the code was inseparable from the act of proving it works? If every single commit was born verified, how would that change not just our tools, but our entire philosophy of how we build software?